Hello, hello. I am very pleased and excited to make this video about UE, my functional programming language. Um, I've decided to include some gameplay in the top left in case the Zoomers get bored watching this, just so they have something to look at. But anyways, without further ado, let me get into the actual language, right? So here's the logo. It's very nice. I had Shimejime on Twitter make this for me. I appreciate it. It's very cute. Um, let me just start with an overview, I guess. So I have this little markdown file with the overview in it. So okay, UE as a functional programming language is based on the lambda calculus, mostly the untyped lambda calculus. For specific reasons, which we'll get into, it's not technically a lambda calculus. It's, I guess, probably more closely related to a lambda calculus with explicit substitutions, although I've not quite nailed down the formalism for what the language is. But anyways, it's basically a lambda calculus. You can think of it like that. Strongly inspired by Haskell and standard ML and a little bit of Lisp. It features lazy evaluation, just like Haskell. It's technically dynamically typed, although most terms don't carry type information, but you can, as a programmer, you can encode that yourself if you so wish. I'll say that it's technically untyped, although the Prelude, the standard library, is strongly typed. That's mostly because the Prelude goes through Haskell, so of course it has to be strongly typed to some extent in that. We probably won't cover the Prelude today. But maybe in a later video we'll talk about the Prelude a little bit. We might do a little bit of the Prelude today. I'm thinking of an example program to do, so there will be some Prelude functions. But the Prelude is just the standard library. It's more or less baked into the interpreter. So okay, now next on the list, right? Applicative records is a feature that is, as far as I'm aware, unique to UE. Probably not unique, although no other mainstream language that I can tell has something like it. Applicative records takes the idea of records from like Haskell and OCaml and turns it into kind of like modules as a first class value. So you can open a module and access the names inside of it, like in OCaml or even something like Lean. And applicative records takes that idea and just says like, okay, what if you can open a module inside of an expression rather than opening a module being something more like a statement. Applicative records turns that into an expression, but we'll get into that. UE also has free constructors, which we'll get into. Hold on. Free constructors. So free constructors, which we'll talk about down here, are like variables, but they're not subject to substitution. This is really useful for encoding like algebraic data types and stuff like that, right? Because UE is untyped, it doesn't have type declarations. So for example, if you're familiar with Haskell and you want to do something like the maybe type or a Boolean type, you would use these free constructors to encode that. And then UE has some limited overloaded syntax, which we'll talk about. That is mostly due to or mostly used in syntax desugaring is where the overloading occurs, right? But anyways, we'll talk about free constructors. So a free constructor is any variable that is prefixed by this single quote character. And so I have this REPL open in this window down here. So I'll type like, here's an example of a constructor, is just quote foo. And then you get back this constructor foo. And so free constructors are always free. Like I said, they're not subject to substitution. So like if you just type in a variable, then UE's interpreter will try to find a value for the variable, which doesn't exist. But foo is never substituted, so it's always just equal to itself, right? And so you use these as constructors for algebraic data types. And so like you could say that, okay, a Boolean is represented as either true or either false, and say that. And there's no type declaration, so every type is technically open in regards to what constructors it has. So type checking is basically a responsibility of the programmer to check that the constructors that a data type receives are what you expect for that type, right? Scrutinized and unpacked via pattern matching. This is because UE has pattern matching. It uses case of just like Haskell does. So we can say like case foo of, and then like say I write a pattern bar. This is non-exhaustive. That won't pattern match because foo is not equal to bar. But then if I have a different pattern here and then say that, this should evaluate to B just like that. Right, so there's our pattern matching. So basically the point of free constructors is to be able to inspect data, construct and later inspect data via pattern matching. Right, so now let's get to applicative records. So a record is a set of key value pairs inside of a curly brace. Technically the names are supposed to be unique in the runtime representation. That's not always true, but practically as the programmer that is always true. And so you can access like this value from the record by using this dot syntax on the record. So like this record.c will give you back this constructor value, or .b will give you back the string, or .a will give you 0. So you can use that dot access, right? And so when we start talking about applicative constructors, we can say that a record applied to an expression then substitutes all of the variables in that expression with the values in the record. So this gives us this equality here, where some record dot some value in that record is equivalent to some record applied to an expression of that variable. So these will both return 5, right? And just to illustrate the point, oh, hold on, sorry. That's because equals is a valid identifier there. And then also x equals 5, and then x just like that. Those are both 5. And so that's an example of an applicative record. This obviously extends way past just this kind of trivial example, which hopefully I can showcase during an example program. But if you've seen like UEBot on the IRC, or you've seen like some of the code that I've written for that, like when we were doing shuffling or random numbers or something like that, then you may have seen something like list. It was like head shuffles some list like that. And this list in the prelude that you see in UEBot is a record, and I'm applying that record to this entire expression because both the head variable and shuffle variable are members of that record. And so this just opens that record to this expression so that this becomes list.head and this becomes list.shuffle. And also, really, this becomes list.xs, but xs is not a variable in list. So it just defaults to whatever the variable was in the scope outside of this expression, right? And so that kind of lends itself to another point. Let me make real quick here. Record application is the same sort of idea substitution-wise as lambda abstraction, in that you can shadow variables. So like, say I just have a record x is equal to 0 and then some expression x. That evaluates to 0. But then if I have another record in here where I overwrite the value of x, then this value of x becomes 1 because this shadows that variable. So that becomes 1. So that's kind of something important to remember. So you can change the scope inside of an expression by applying a record to it, but you can't retroactively like change the scope outside of that expression. So that's why I have the phrase dynamic-ish scope, because it's not quite dynamic. It's still, I don't know if I want to use the word lexical scoping because that may not be true, but it's not fully dynamic scoping. But this lets you do stuff like first-class modules and things like that. So I don't know if I have a good example of that in the prelude, but something like if you want to write a like an ordered map, using a record, then what you could do is say like, okay, I want to declare a kind of map module, right, that takes an ordering function for the keys, and then it returns a record. And then, you know, you could have an implementation like, okay, insert some key and a value into a map, and then you can, I don't know, inspect on a map, and then you can use this ordering function on the keys and stuff like that, whatever. Anyways, that map ordering becomes a module that you can then construct for different instances of this ordering function, giving you a kind of gives you a module, so you can use it kind of like type classes in Haskell. It's really very close to the idea of modules in standard ML. So if you're not familiar with standard ML, which I'm not super familiar with it, but the modules kind of work like that. Really the only difference is that standard ML is statically typed and it doesn't have applicative modules, but otherwise the module system is very similar. So sorry if that was confusing. I didn't make a script for this or anything, I'm just winging it. So anyways, overloaded syntax. So UE has two forms of syntax that are overloaded. There's list literals, which are done with square braces here, like that. And then there's do syntax, which is very similar to Haskell's do syntax for monads. And so these are overloaded in the sense that they desugar to literal calls to these functions, nil and cons in the case of lists, and pure, bind, and m0 in the case of do. And so m0 is not something that gets called very often. It's basically an error function, but do is something that frequently fails, so it's useful to have an m0 in scope for that. That kind of goes back a little bit to the legacy cruft that Haskell had with its monad instance, where it used to have the fail method, although that has since been taken out a long time ago. This is kind of probably the same sort of historical misstep as that, but anyways. So list syntax desugars to cons and nil, so a list literal like 1, 2, 3 it literally becomes this expression, cons 1, cons 2, cons 3, nil is the empty list. And then do syntax also has this additional keyword with that just becomes an application of its expression to the remainder of the expression. And so this do expression desugars to this expression here. And so bind, if you're familiar, is the monadic bind. Pure is the monadic identity. So yeah, I don't know. That's about it. That's what I've got for the overview. Now I think for fun, what I'll do is write a quick example program, and then after that example is done, I'll make another video expanding that example program and adding some additional things to it just for fun, in case you're still curious about how some things work. But anyways, you may have seen, probably not, but another video on my channel is an implementation of normalization by evaluation for an untyped lambda calculus, which I wrote in Haskell. I'm going to do the same thing in UE now, or at least attempt to, just as an example of how the program works. So first off, what we'll do is we'll define a record for our namespace, and then I will just, we don't have to declare data types because UE doesn't have any data types, so I'll just start with the evaluation function. So we have our namespace, and then we have an expression, case expression of, and this is going to be a untyped lambda calculus, so it only has variables, lambda abstraction, and application. So I'll just go ahead and write these out here. Abstraction and application, like that. Okay, and then now when we get to a variable, we want to look it up in the namespace, so I need to write a lookup function for that. So let's go ahead and do lookup key in a list. Normally with a recursive function in UE, I would use a fixed point, but an important thing to note is that when you define functions in a record, it's a mutually recursive environment, so you can define values in the place, or that depend on other values in the same record. So I'll write this recursively instead of using a fixed point, although you tend to prefer using a fixed point. But anyways, case XS of, I'll write this down here actually, case XS of, and then we'll pretend that our namespace here is a list of tuples, k prime v XS, like that. If the list is empty, then we return nothing. And then we can write a guard here. So I'll write a guard equals, the prelude is in scope by default when you call the interpreter. So it's referenced by the name prelude. I'm going to apply the prelude record to this record so that any variables in here can reference variables in prelude. So here's another example of applicative records. So if the key that we give here is equal to this key, then we will return the value, and then otherwise we will recurse and look up what's in the rest of the list, just like that. So now we can do this, case lookup x namespace of, nothing. And so I'm not going to go through the idea of normalization by evaluation here, but in this case what we have, if x is not a variable in here, then you could either fail completely or say that it's a neutral variable, which is what I'm going to call it. So I'll call it neutral, and then a neutral variable is just an expression, or a neutral expression is just an expression, so we'll just rewrap the original term here. And then otherwise we get back a value, so I'll return the value. There's a lot being unsaid about normalization by evaluation. I'm just going to implement this. If you would like to learn more about this, I can recommend some reading materials. But this is a pretty simple implementation for untyped lambda calculus. But anyways, let me continue. When we evaluate a function abstraction, we return a function that takes a value, and then we evaluate the expression in here, and we bind this value to this name. So I will add it to the namespace as a new key value pair, xv, just like that. And then now what I'll do is I'll define a little helper function here. Go x of. I've not really settled on like a uniform kind of like code style for UE yet, so you may see me kind of messing around with spacing and stuff like that every once in a while, but anyways. So when we evaluate, we either get a neutral or we get a function. Those are the two values that we've defined so far. So I want to evaluate the left-hand side of application first, and then we can either get a neutral value or we can get a function out of that. So, and like we see here, a function, this value f takes a value as an argument, so we will just apply f to the result of evaluating the right-hand side of this application, like that. And then if we have a neutral value, we have to propagate the neutral value. So what I'll do is I'll use this prelude function composing. Composing itself is a record that defines nil and cons in terms of function composition. So a composing list literal is using overloaded list syntax to write a composition of a series of functions. So neutral app x prime. Then we want to reify, which I have not defined yet. Go y, just like that. So then now let's define this reify function here. Reify function, if you can trace the types in your mind, should tell you that this go gives us a value of neutral or func, but an application is going to be either a var, an abs, or an app. So reify is a function that goes from neutral or func to one of these three types in the Lambda calculus. So let's go ahead and write this. I'll use a fixed point for this. Don't worry if this is confusing. I've written these evaluators probably 3 or 4 dozen times. Although I'll be embarrassed if I say that and then this doesn't work the first time, so just maybe ignore that I said that for now. Let's see, when we generate here, when we reify a function, we need to generate a fresh variable name. So I'll just say that it's a function of some number n, which we can generate here. And then this f is a function taking a value, so we need to turn a string into a value, which we can do by turning it into a variable, wrapping that in neutral, and then we can apply it to that function. And then we have to reify it again to construct an expression. And so since this is a fixed point, this here is our recursive reference. So I'll call rec int.add n1, so then this increments this number by 1, like that. I think that this should work, hopefully. Here's our evaluation. Now, let's write normalize, reify, evaluate, nil, just like that. Let's write a test program here. So let's say that we want to apply I'll just write a very simple one for now. Apply okay, I think that's right. Let's while we're at it, let's write a pretty printer for the Lambda calculus too. Pretty expression here. So hold on. I'm going to write this as a fixed point as well. Okay, so for our variable x, we can just return x, which is a string, right? The idea is that we can return a string here. I'll annotate its type, so. Actually, I'll go ahead and type all of these. Okay. Let me think here. Let me define a quick helper here. This I'm going to use as a list literal overloader. List literal overloading is good for any right associative monoid, for lack of a better word. A list literal is a free monoid. Anything that is a monoid you can use list literals for pretty well. So string concatenation happens to be a monoid, with the empty string being the identity, cons being the semigroup. So there you go. There you go. Pretty simple, you think about it. Concating x, actually backslash x go 0 y, like that. I think that gives me what I want. Okay. And then here we will use the new keyword cond. Cond is kind of like Boolean conditionals, only it doesn't take exactly Booleans, it takes guard expressions, which may be Booleans, but they may also be patterns. In this case, we will be using patterns. So let me think about this. We have precedence. Application is strongly left, binds strongly to the left. So if, I never remember what order to put these in. Let's see. Compare if 9 is less than prec, then we need parentheses. Otherwise, okay. Go 9x, go 10y, like that. Okay, I think that might work. We can actually, let's open this up in a REPL and let's try it out. Let's do UE, oops. Oh, alright, this works. Actually, just kidding. We'll do it here, in this window down here. UE, lambda. Oh, hold on. I'm missing something. Right arrow, name, evaluate. This is the quality of error messages that I'm trying to improve, by the way. It's pretty bad. Oh, there it is. I was writing a Haskell style lambda. This doesn't use right arrows, it uses dots inside the lambda. Okay, there we go. Alright, now let's try pretty zero program. Okay, that is not quite correct. Let's do, what we need to do is check the precedence here too. Maybe that works. I'll be honest, pretty printing is not my strong suit, even though it should be something that is not very hard, but I'm not quite good at it. Because I never remember how the precedence is supposed to work. Okay, let's try that. There we go. Okay, that looks good. That's better. Now let's try... I want to try one more thing too here. Let's do pretty app var x app. Okay, perfect. That seems like it works. Okay, never mind, just one more thing. Let me try one more thing. We're debugging our pretty printer here. Very soon, this demo will be over, just bear with me. Okay. Okay, now let's run this here. So let's say main is equal to composing put string line pretty 0 normalize program dot main. Perfect. So now this normalized to a function that takes another variable and then returns this x, which is exactly what I wrote, because this here is a function that takes two variables and returns the first, but this is only a partially applied function. So if I wrap this in another application, oops, I keep pressing the wrong thing. Now that's fully evaluated and it just gives us x back. So there you go. There's an example of a program written in UE. It is a normalization by evaluation of an untyped lambda calculus. Now, I think I'm going to end this video here, and then I might, if there's interest, make another video where I'll extend this and I'll write some parser combinators, and we can actually parse these expressions out of a string so that you don't have to build it like this. But otherwise, thank you very much for watching. I hope you enjoyed this video as much as I enjoyed making it. And let me know if you want to see any more. Bye-bye.